So, as I promised, this is the last part of lecture 5 in which we're going to cover charge transfer transitions. So this point is a moment in which the ligand is actually doing something. So our point to trigger this increased conversation was that ideally at D0 and D10 with no electrons available to do the jump within a sensible energy range should give you something colorless. This is countered by the very compelling and incredibly color evidence of permanganate that gives you an incredibly purple substance coming from a D0 metal. So why is this thing so colored if there are no possible electrons? So since this is an O4, the arrangement should be tetrahedral. What are we looking at? So if we look at the molecular orbital of permanganate ion, you need to get the oxygens and you need to get the manganese. So at this point, what you get out for yourself is a tetrahedral molecular orbital diagram in which you can see clearly that my PowerPoint presentation crashed, so I apologize for that. But I was saying that since you have manganese and oxygen, then you need to build the molecular orbital diagram that is a tetrahedral molecular orbital diagram this time around. This gives you a different set. So the set that you get is the anti-bonding orbitals that in this case are primarily metal-like. So they come from a mixing of the metal and they are closer in energy to the metal. So this thing will be your crystal field splitting. You can see the set of the E and the T2. So this is what you will get with manganese and oxygen. This will be where they will be at. But then you also have a second set, because this one is empty. This is exactly what we were expecting. We know now why it is so happy to be empty, because it's an antibonding orbital. So everything will be going out. We know permanganate is perfectly fine, even in such a high oxidation state. But you have another set, and this set is non-bonding orbital. So they are not mixing because you mixed the previous one. So you end up with a set of non-bonding orbitals that are ligand-like because they're in the molecular orbital, but they are coming from the ligand. And these orbitals are full. They are chock full with a bunch of electrons. So this is the arrangement that you get yourself in when you look at the molecular orbital diagram of something like permanganate. So what are the observed transitions that we get? If you do the UVVs of permanganate, you get yourself 4 different peaks at different energies. So I've ordered them from higher wave number to lower wave number in centimeters to the -1. So this one is the T2 to the T2 star. So you get this threshold here, you go to the highest possible one, which will make sense. So higher wave number, higher energy, lower wavelength. The second highest must be the T2 to the E. So you're starting from this, either you go all the way up or you go midway up. The second option is you don't start from the lowest, you start from really the frontier of the HOMO. So you go from T2 to, T1 to T2 star. So again to the highest. And the last possible option, you go from T1 to E. So you can see how this is accounted for, but it requires you to start from this non-bonding orbital. So these are the transitions that you're seeing. They're all accounted for and they all make sense. So all of these things, since they are going to d orbitals, but they're starting from ligand orbitals that are primarily oxygen-like, so they are primarily p-type, you go from p to something that is primarily d, you are perfectly Laporte allowed, and since all of these orbitals are completely empty, you find yourself with a spin allowed type of transition. So this is going to be very happy. And this one is the only one of these transitions that ends up in the visible range. And this is the one that gives you the color purple. So this is the one you see. And this can give you the feeling of not only the electrons are coming from the ligand, it's the ligand that is providing you the electrons to go, but also this thing is incredibly intense. You know it from permanganate. You know how purple it is. This is a very, very strong transition. So this is what we called a charge transfer transition. So you must get this charge from somewhere. Your electrons are not coming from the metal. They're coming from somewhere else, but you're using them to transition. So this is what we call any type of electronic transitions in which the orbitals that are involved are centered on different entities. So the orbitals are not the same thing. They're not the orbitals of the metal. They are partially the orbitals of the metal and the other orbitals that are fundamentally more of the ligand. Given the nature of the orbitals, these things become Laporte allowed because it will change significantly the angular momentum of the type of orbital that you're using. And usually, since you're landing on empty orbitals, this will become spin allowed. It will dominate any spectra of any complex you have. If you have a complex that is displaying a charge transfer transition, it's over. That's the one that is the strongest. So in D0 complexes, which is the one that we've seen here, you can only have what we call a ligand to metal charge transfer. In other complexes, you can have a combination of this factor. So some will only have DD transitions, but you have other options. You can have the ligand to metal charge transfer once again to partially filled orbitals of the metal, or if you have available levels higher than the one of the metal, then it becomes a metal to ligand charge transfer. So it is the metal that is going up again and reaching up with the electrons into a level that is higher in energy, but primarily the one of the ligand. So you have a lot of ground, way more ground than the DD transitions. And you can see that DD transitions are always the one with the smallest gap. So it's not that big of an energy gap. And these ones instead are going to be massive. And sometimes they can come with a lot of very pretty colors. So if we consider the ligand to metal charge transfer in octahedral complexes, I told you they dominate because they do. So when you see a full spectrum, it's not that you don't see the potential DD transitions of your metal. So this is the DD transition. Depending on what options you have, you see multiple peaks or a single peak. But they are at a completely different energy range because this is a tiny jump in comparison to the ligand to metal charge transfer. And you can see the difference in intensity. So this is 4 times higher than anything you could get from the metal. So if your complex can trigger a metal to ligand charge transfer, it will do that. And you will see it, especially because you can imagine you cannot stop your complex from displaying such a transition. And if this transition is in visible range, this is the thing that will give you an immediate color because you cannot stop yourself from seeing that this transition is happening. How do you know if you're looking at the charge transfer type of transition? First point is obviously the intensity. If this is too strong, then you should be immediately suspicious that you're looking at a charge transfer type of business. The second thing, if you are able to do experiments at different temperatures and in different states, given that you have different entities interacting, and some of these entities will have this like sigma orbitals or pi orbitals bringing in everything, if you go at low temperature or in a different state, so gaseous state instead of solid, instead of liquid, instead of whatever you want, you end up seeing the fine structure of the transition. So the moment in which, instead of having a general peak, you start to see how these levels can be slightly differentiated around the right peak in a sort of statistical distribution of vibrational level and rotational levels. Another very important thing that is related to the charge transfer transitions is that they can be influenced by the solvent, which is something that you will not consider for a metal, because why would the metal care, the metal center, why would it care if there is a solvent? But the solvent interaction here is actually changing what is going on around the whole complex, because you're not focused on the metal in its crystal field splitting, you're focused on the whole complex in its whole molecular orbital diagram arrangement. So if your excited state is polar and you put something from non-polar solvent to polar solvent, you're changing the threshold of these orbitals. So the change in polarity of the solvent can influence a charge transfer transition, because it is influencing the electron density around the complex, and this distortion of the electron density around the complex, either better or worse, is going to move these levels around. So you need to consider what type of solvent are you using against what type of complex. Neutral versus polar versus non-polar is going to tell you something about your charge transfer feature, because it will be influenced in a different way. If your thing it can be influenced by polarity, it will. If it can be influenced by non-polarity, it will. So we said before that we can have two different things, the ligand to metal and the metal to ligand. So you're taking two different approaches here. So the ligand to metal charge transfer, you're passing from filled ligand orbitals to empty metal orbitals. When you do this, you're fundamentally adding electrons to the metal, which means the metal must be happy to be reduced. And you're removing them from your orbitals of the ligand, which means your ligand must be sort of happy to be partially oxidized. If they're really not up for this, then the likelihood of the transition will go down. This can only happen, inevitably, if your ligands are good sigma or good pi donor, because you must have this arrangement that is proper in energy and is leaving empty and full energy, with the metal being higher than the one of the ligands. So something like this, like in the octahedral molecular orbital diagram that we know how to derive, you end up with the non-bonding T2G, the anti-bonding EG, and the one of the sigma donor that go low. At that point, you use all of this to transition into the anti-bonding. In a metal to ligand charge transfer, you're doing exactly the opposite. So you're using the filled orbitals of the metal and the empty anti-bonding orbital of the ligand. So your metal is getting oxidized as you're doing this, and the ligand is getting reduced because you're adding it electrons. So you must have a certain likelihood that this thing will happen. So this thing can only happen inevitably if the pi star level of the anti-bonding that you created is not so far away in energy that is not triggerable by the UVVs. Otherwise, you will not see it. You will have to go to higher energy to be able to probe it. So it must be accessible and it must be empty, and then it can be correlated with the electrons coming from the d orbitals of the ligand, of the metal, sorry. If you want to see a more textured view, which can also help you figure out why do you have so many possible sublevels and so many peaks that come up, this is a version with the ligand, metal to ligand charge transfer. So, and this one is the one with a ligand to metal charge transfer. So which jumps you're doing will depend on the system, but this is a more textured view. You can see that this is just an expanded version of the molecular orbital diagram in a simplified version that we had before. But at least we know where the electrons are coming from. And what do we mean when we say the energy must be achievable? You cannot be that far, too far away. But these ones in the ligand to metal charge transfer must be filled, and these are empty. And instead, in the metal to ligand charge transfer, these ones are filled and these ones are empty. So an example that is not permanganate of metal to ligand charge transfer, whereas permanganate had the ligand to metal charge transfer, is the ruthenium. So this tris-bipyridine ruthenium 2 complex is very prominent, it's very pretty, is used for a lot of very important applications because it's a nice sequence of bidentate ligands, so it can be used for a lot of further functionalization. Very, very, very bright red, impressively bright red. This is coming from the field, the orbitals of the ruthenium going up into the bipyridine ligand, which is a strong ligand, which makes it a pi donor, a very strong pi donor, which will make empty level of the T2G achievable. This example here is made with iron bipyridine complex, but the concept is exactly the same. So the transitions that you're seeing are this one. So this one is incredibly strong. Everything else, yes, it can happen, but it's at a different energy range and much, much lower in type of intensity. So your primary one is the one that goes from here to here. Other things are weaker. Extra special cases that we want to consider because they can have an influence is the metal to metal charge transfer. So the metal to metal will require you to have metals in different oxidation states, otherwise they cannot talk to each other. But this is the reason why if you have a compound with mixed valency, is going to be colored, strongly colored, because you are transitioning electrons from one point to another. This is the example, for instance, of Prussian blue. Very nice blue color, but the one that is blue, as per definition, is the one that has the bridging framework that is bridging an iron 3 and an iron 2 and an iron 3 and an iron 2. Since these metals are talking to each other, they can transition electrons around. If you have a version in which instead of having iron 2 and iron 3, you only have iron 2, your compound, same arrangement, is white. So it's out of electrons that can go in transition. Same thing if you have lead oxide. Lead oxide with only lead 2 is very vaguely sometimes yellowish, but fundamentally white. The moment you do a mixed state, because lead doesn't have a 3+ oxidation state, it can have 2 and 4, but then this one has a half-half 2, half-half 4. You start to transition electrons across, and this gives you a nice bright orangey type of tune. For the record, you also have ligand to ligand charge transfer, but these are a bit more exotic type of business because you kind of need a conjugated system of the ligand that will be colored by itself. So we are not going to cover it, but you need to consider that electrons can transition everywhere they can find available level. Remember, when you do these type of configurations, that you need to have the impacts of everything. So everything we discussed so far will influence, because the charge transfer effect is just an effect of where are your orbitals. So you must still have all the considerations that lead you into having a difference of energy levels between your metal and the ligand and stuff like that. So you must not forget what metal are you using, what is the period and what is the group, what is the oxidation state of the metal, and how big is your ligand, and how much overlap is it going to have with the metal orbital, because all of these things will change the available possible energy ranges, and it might bring something in or out of visible ultraviolet range, which will make it visible or not visible also to human eye. So at this point, I hope you appreciate that we know now where all the colors that we appreciate in a lot of paint, in a lot of substances, in a lot of plants come from. So this is an example with some very inorganic type of thing, but as you've seen, you can have the same effect with a nice, more organic base ligand and the metal. So every time you see a color, most likely you're looking at the charge transfer type of business. And if you're looking at a charge transfer type of business, you now know how to conceptualize it. To conceptualize it better, this is a big slide of summary of everything we can have in terms of DD transitions, metal ligand transfer, the ligand metal transfer, and everything else. So this is a very busy diagram. You know that not every type of system is going to be able to do all of them, but if it is able to do all of them, you're very likely to see all of them. This concludes lecture 5. Please mind your learning objectives for this week. And I will see you at the Q&A after you're done with your tutorials. Thank you.